Hit it, baby.
Well, hello. We got cut off there for a minute. We're not done with trigger.
Hey guys, this is Trigger Part 2. We're still gonna
Yeah.
post it up. Still comes in the same package. Don't worry.
We're going to keep going. We're going to keep going. So, uh, let's just go over a few random important bits about trigger, which will be if my ECU wants to cooperate. Come on. Come on. Come on, dearie.
That poor laptop has been a workhorse. She's done great.
Yes, it is. She suffers. She has suffered. She
So,
has
so
suffered
we
dearly.
we've gone over the understanding of trigger angle and TDC offset. Um,
Yes,
Offset being the
couple of
numbers that
sensor
we're
types, and then eventually, just we wanted to close up by just talking a little bit about effectively what's involved in the trigger setup. So we'll scroll down here real quick, and then we've got obviously in the Haltech software scheme of things, we've got a trigger signal. We've got a home signal, which is what Haltech calls the crank and cam reference. Home being the cam, trigger being the crank. You have your options to select your type of sensor, reluctor, Hall, custom. Personally, I try to stay away from custom unless it's absolutely necessary and it's not some funky, weird sensor that just needs extra conditioning. 95 or 98% of the time, it's either reluctor or Hall, and you can get away with these settings, no problem. If it's Hall, usually you want to enable the pull-up. The only time you wouldn't if you're doing a parallel installation and the factory ECU still has to be retained. And then of
now.
course yeah, go ahead.
Correct me if I'm wrong, but on some Hall effect sensors, you're actually wiring in a resistor external, and
Only if your ECU does not come with it. And
exactly.
most of them do.
And that's why I'm saying this. So the pull-up would be
Yeah.
you might not have this option for your ECU. So you're actually having to add a resistor to your Hall effect sensor to give it the correct, what would you say, the correct feedback to
It's
have
the correct voltage so that it
correct
climbs
voltage.
up to where it needs to
Yeah.
be. Yeah, that's what the pull-ups do. They take you splice them into the power wire via the resistor to the signal wire, and what that does is it basically makes the signal go up to that pull-up voltage, which most of the time you would use a 5-volt pull-up. You can use an 8-volt pull-up or a 12-volt pull-up. Having said that, normally the Haltech ECU, the Link ECU, the Mtron ECU, the Motec ECU, they will have a built-in pull-up, and this is not needed externally. One example of where we would use it is if we were wiring, for example, a speed sensor in an ECU where the extra digital inputs don't have that built-in pull-up.
Right.
Yeah.
So one thing on the voltages is personally I found that the sensors will operate better at higher voltage. Normally I've seen ABS sensors do best at 8 volts or 12 volts as reluctors, or even Hall effect doesn't matter. But every time I've seen sensor voltages higher, I typically see a clear signal from that. Claudia, do you have any experience on that?
So if we're talking specifically about crank sensors,
Mhm.
they're they're let's call it they're easygoing. A 5-volt pull-up will tell the ECU enough information to work normally, especially if the signal is clear, no matter what RPM. Where you would probably look to use a different voltage or a 12-volt pull-up is if you didn't have access to an 8 or a 5-volt pull-up in the first place. Or if we're talking speed sensors, sometimes we need to do the reverse, which is a pull down. And it's a little bit of a tricky situation, and we should leave that off to when we're doing like extra sensors and advanced features.
Yeah, that's
So
much more advanced.
yeah, so but most of the time you will be fine with the internal pull-up or a 5-volt pull-up or an 8-volt pull-up. And most advanced ECUs will have that 8-volt wire, which is usually there for this purpose.
Yeah.
Yeah. So one of the things that pop up when you select reluctor sensors is the arming voltage. And these base tables that the software comes with are usually a good starting point. Some Toyotas will probably want a lot less voltage up down here in the first couple RPMs. I've seen them go as low as 0.1 volt to get going. What will happen is you crank the engine and you get a 0 RPM, or your cam sensor is not reading right and you get RPM, but you don't get sync. And then you're using the diagnostic page here with these two messages, the trigger sync level and trigger sync state. These will tell you if anything is wrong. If they don't say running and full, the computer is not reading both signals correctly and it's not doing full sync to fire the engine right. Usually one will give you an indication of what's going on either the home or the crank. No RPM, for sure crank. Home issue, no sync, no spark, then it's probably a cam.
I was going to say there is also a threshold for when you go to crank the engine on the engine starting threshold. Sometimes this is set too low. So let's say you have an aftermarket Wasp starter that spins at some crazy high RPM. It should be under engine configuration, Claudio. This right here, this maximum cranking RPM. Now, if you have a very fast starter and it's exceeding this RPM, it's going to actually cut the engine off before it catches. So you'd want to bolster this up to a higher number, let's say 450 or 500 RPM. And that way it's not cutting out during the starting process, and then it doesn't have a catching of the engine. And some engines are just harder to start than others. So this is kind of something that could be a fault. Just
the other point to this value is this below this is where the ECU is doing cranking timing, is doing cranking fueling, and if it's either too low or too high, then it gets crossed over with your corrections or not. So let's say for argument's sake, your starter is just winding at about 120 RPMs. That's a bit too low. But if it goes beyond 380, you've got one badass starter, and then of course you've got to play with it, because then the ECU just thinks it's running, and it deviates from the cranking parameters. So you may, and if it's cold, it won't start because you probably didn't put enough fuel in it, timing is incorrect, et cetera, et cetera. So always play with that.
Let's go back to our trigger settings real quick. I want to show them something that they can use as a quick and dirty way to figure out these voltages. So these are never going to be perfect for everything, right? But let's say you're cranking the car and your RPM is showing up and it goes from like 200 to 500, 200 to 500, 200 to 500. So that means that our threshold for 500 is not high enough. Because if the engine is actually only turning, let's say 250 RPM, then, and it's showing that it could be technically hitting this threshold of 500, that's giving you an idea that this is too low of a threshold and it's hitting higher voltages than that. And therefore, that's why we have value where it needs to be increased to clearly read an actual RPM of the engine.
One of my rules of thumb for these voltages is usually you want these values to be about a third of what your total oscilloscope voltage is. Let's say you got 2 volts during cranking or 1 volt during cranking. A third of that is about as low as you want to go. And then, of course, above that, you know, you're not clearing it. It's not giving you a proper signal. So you could see, for example, let's say that the engine reaches 500, but the threshold is set too low. And then you'd probably be getting, an over signal. And then what the ECU will do is say, well, this peak went too high. What do I do? Is it a signal? Was it an edge? So you probably want to stick to that formula of about a third of a volt or a third of the value that you want, that you have on the oscilloscope.
So in the condition that the engine is not revving fully out, the first thing I would do is I would take these values and I would increase them by 0.2% or 0.2 on their value of voltage. And if it gets worse, you could try to measure this either in a log or just by looking. if it gets worse, you've gone too far and you have too much filtration of the trigger arming voltage. And what you'd want to do instead is now start dropping it down by maybe zero point 0.2 volts at a time until you get something to where it is revving cleanly.
And then the other thing, since you mentioned filtering, we've got this filter value, and usually 9 times out of 10, you don't need to touch this. This can stay at 0. You're fine with the arming voltage. I have seen this needing to be tweaked on old wiring, old distributors, or old crank angle sensors that are just bashed and bruised. And that's when you usually have to tweak these. However, the scope will tell you if this needs to be turned on. Let's say you see a signal and there's a lot of ground noise in the middle, or there's peaks shooting way beyond the range that you've got your arming voltage. Then you probably have to cap that off with the filtering. So think of the filtering as an upper cap, and then the voltage threshold or the arming voltage is a lower cap. But you never want to go too low on the arming voltage, because then it's going to probably just look at ground noise, and that'll confuse it even further. If you've got a sensor going so low that it will never go beyond like a 0.2 or 0.3 volts, that sensor's probably bad.
So one thing we haven't mentioned yet is spacing of the sensor to the trigger wheel. There
Yeah.
is a data sheet for each of these sensors, whether it's a GT101, a cherry red, whatever it is.
BMW.
Yeah, just whatever the sensor is, there's going to be a tolerance range in which it can read a certain amount of RPM per second. A certain distance is ideal for air gap. That's what I'm talking about, is air gap. And then we also have on the trigger wheel itself, if you have an aftermarket custom trigger wheel, well, the spacing between those notches and those gaps is a specific necessary spacing. Now, some of these companies make these too tight together or too rounded or whatever the case may be. And that will also cause these weird false signals sometimes.
So it's not a question of going, oh, Hall effect is better. No, your wheel needs to be properly machined, and the sensor needs to have a proper gap. Because one other thing to mention about the gap is a small gap works great at low RPMs, but at high RPMs, it's going to drive the sensor voltage through the roof.
Yes.
Then a bigger gap works great at higher RPMs, but then it'll cause a whole bunch of trouble down low.
It's so funny because we can almost relate that to spark plug, similar sort of thing. It's
the tolerances.
The tolerance is important to be, I would say personally, I've set them on the tighter side of the halfway point, but not the base of the tolerance. So if we have recommended between 20 and 60 thousandths of an inch, 40 thousandths of an inch would be our middle ground, and I would aim to be between 25 and 30 thousandths of an inch for my ideal placement. That's me personally.
As we all know, everybody gaps those 2Js at 0.02, 0.016.
Yeah, so
they tied them tight.
And that gap I'm referring to is in regards to the crank angle sensor gap to the trigger wheel.
Yes, of course.
Actually, let me pull up. I'm going to pull one up real quick. Trigger wheel. No.
You can probably Google an image that has trigger gap and a little measurement in there.
Yeah.
It's a balancing act. It is close enough to get clean signal at idle, and not so far enough to where you don't get so much voltage coming from the sensor at high RPMs that causes your arming voltage to not be at spec, or the filtering needs to be engaged. The less you have to depend on filter, the better.
Here we go. And okay, so right here we're talking about the tooth distance and the width of this tooth, and then this spline width as well.
Mm-hmm.
And then if there's a squareness issue, so let's say that the tooth somehow got rubbed against something and now is dull. Well, that's going to affect, especially if it's in a vertical sense like this, it's going to affect the
The
reading
field.
quality. Yeah,
Yeah,
the field,
the field.
the magnetic field of this. So this explains here a falling and rising, right? If the tooth is going this direction versus the tooth going this direction, and it kind of shows what this does and then how it interprets it as a digital, right?
Yeah. Yeah.
And then
So
we
effectively,
also,
if we were to scope those two teeth scenarios,
Mhm.
as a reluctor, it would do one thing. As a Hall effect, it would do something different, obviously. But the if it's a tooth or if it's a hole,
Right,
obviously the resistance goes one way or the other past zero.
right. And so this one's interesting. They have, this is not the ideal one, but this is a 3,600 RPM or less GT 100 or 101. This is something for like a wheel speed. So this would be probably a Ford ABS sensor on a wheel.
I mean, in theory, you could run that with a 12 tooth. You're
Yeah.
probably still fine.
And this is an air gap of 40 thousandths to 80 thousandths for its test condition. To me, normally on these sensors, they like to be closer than that. But like Claudio said, better at low speed when it's tighter, not as good and overdriven at high speed when too tight. So just kind of play with it. Definitely something to look at. And I think that gets us mostly done with trigger stuff. No?
It's one other, yeah. The what you call it, the number of teeth versus the RPM is kind of probably why Bosch uses.
We're back. My
Well,
goodness.
hey, we're back again. We're not done yet.
I had a blue screen error of death. I had ESOD. Take it away
I'm
from
not
you.
frozen.
Yeah.
Anyway, just it was. So I felt sort of cut off there for a minute,
Yeah. So
talking to myself. So, quick summary of what we've talked about in this lesson, so we are all on the same page. We've discussed how the different ECUs tend to approach somewhat similar, how the cranking cam sensor are read, are conditioned, monitored, and of course you get diagnostic messages in the different ECUs that help you troubleshoot. We've talked about arming voltages, where you want to look at your voltage coming from your sensor using the onboard oscilloscope. And that way you can trim these arming voltages so that the ECU always gets a clean signal. If you see too much noise, check your wiring, check how the harness is laid up, make sure that you've got the necessary setup correctly, so that way the ECU will understand your crank and cam based on the parameters in your trigger setup, so that it in turn can process the information correctly. So good data in, good data out. So the next point to cover basically was our sensor types. You need to know exactly what sensor you have. So 2-wire sensors, always reluctor. 3-wire sensors could be Hall or reluctor. One of them usually is just a shield. And then Hall effect sensors will be 3 wires, a power, a signal, and a ground. Eventually, you have 2 types of installations where the standalone is controlling everything, or you have a parallel installation where you have to share the signals with the stock ECU. If you're sharing signals with the stock ECU, if you remember, we spoke about pull-ups. Those have to be disabled so that the signals don't get crossed and confused, and not even the stock ECU doesn't work, or the standalone won't work. The same applies for speed Hall effect sensors and temperature sensors.
you can kind of compare that to putting a low pass or high pass or band pass filter on an audio file system. If you're trying to run a full signal output from something in a full true range, and then now you've added a pull-up, well, the effective comparison is now it's not that full range that's going to the device you're trying to give it to. So that's why he's saying disable everything, give it its raw form, and therefore can now relate the same information back to each device.
Yeah, because if you leave the pull-ups on both sides, obviously it just creates a incorrect signal that none of the ECUs can use.
Right.
A telltale sign of, for example, temperature sensors that have the two pull-ups on for both ECUs is the range doesn't change, or the temperature reading is really off from where it needs to be when you know you've calibrated it correctly. So watch out for that. And eventually, to get the ECU to be in sync with the motor, grab your timing light, enable the function called lock timing. All ECUs have this, where it just tells you lock yourself at this value, usually at 0, which is what you will have on your crank or crank pulley. If you don't have any marks on your pulley, one thing to try is to line up the cam belt with the cam sprocket, or if you have the long rod, you can stick it inside the engine and find where TDC is. But this method isn't really that good because you could have a plus or minus gap of timing that wouldn't be 100% accurate. So once you know you've got TDC, you can make a mark on your crank pulley if the engine's at TDC, and then you can start from 0 to figure out your timing.
There we are.
Trigger
So
setup.
we would be
The
changing our
lock timing
angle here.
option goes in the ignition settings or in the ignition tuning.
Yes. So for Haltech, let's say that we have an FD crank trigger wheel. We know that we have one of that little triangle thing we showed you guys earlier at 20 degrees ADDC. So for us to not have other opportunities to measure something, we put the timing light on trailing 1. We then put our firing angle at -5 with a 15-degree split. -5 with 15 after it now makes 20 degrees ATDC.
A word of caution before you continue.
Yeah.
It's -5 and +15.
Right.
If you think about your old math algebra, -5 minus 15 gives you -20. And -20 means after TDC. If you have anything other than this, this will create an incorrect position and your final TDC value won't be the same. In a rotary, usually your TDC offset will be 5 degrees in the trigger setup. So if you have to deviate from that, let's say you have to go 15, 20, 30,
So
then you know
FFE,
you've got something out of place.
Right. An FFE trigger wheel is going to be 0. So you're going to put this out to 0.
Isn't it 90 on FFEs? I thought it was like
No,
90.
you
95.
set your firing angle to 0 on this, and then you go into your ignition, your trigger system here, and this is going to start at 90 for the FDs.
Yeah, that's
and then
what
it starts at 60 for the FCs. So that will get you your base reference angle to start from. But in the scenario of the FD crank trigger wheel, this will start at -5, and it is called trailing for a reason. It is following the leading timing. That's why it's 15 degrees after. Just want to clarify that. So we lock that. Once that is locked, make sure you turn this off. It's orange, gold, whatever you want to say. It is shouting at you, don't forget me.
Don't leave it on, or you're running at -5 degrees of timing, and that'll probably heat up your exhaust.
I was going to say, Claudio, have you seen 2000-degree EGTs before? Because I'm sure someone who left this on did. So I have one more thing to show you guys on screen sharing. Give me just a moment. We're going to hop over to our other trigger here. This is a much more common one. This is our cherry red sensor, now owned by ZF. These look like this. They have an adjustable, and I think there's some oddball like M1 by 1 or something. It's a really cool configuration. Yeah, it's M12 by 1. But that means that every singular rotation of that gives you exactly 1 millimeter spacing difference. Oh, let me pause it.
What happened?
My camera.
And we're back.
Camera died again. Okay, so we're gonna screen share just for a moment again on the sensor. Here we
What's your point
are.
about this cherry thing?
Yeah, chatty sensor. Okay,
I'm still
so
hungry.
we've got. You still didn't eat yet. Jeez, we've been at this all day, guys.
I did, but I'm still hungry.
So this will show us, it can handle certain vibrations. It can handle certain 15,000 times per second that is a very, very accurate sensor.
I think I don't want to bash this because I like the sensor, but I think the sensor doesn't like heat too much.
It does not like heat.
Yeah, so mind you guys, if you use this near exhausts.
And it says right here in this temperature, I'm not sure if you guys can see everything, but the screen sharing should be on. Claudia, are you seeing the full? Yeah, okay, yeah, you're seeing what I need to. This
Yeah.
is only showing a maximum 221 degrees for engine bay temperature for the standard sensor, the 501.
Yeah.
Mine is, I believe, a 502, and I have 320 gauge wires off of it. But yeah, temperature sensitive, definitely. Normally at the front of the engine, you should have a fan nearby, so you're not going to have a problem with that. But who knows? Depending on where you put it, if you put this on, let's say, an ABS sensor, and of course that's next to the brakes, and the brakes get extremely hot, this will be a little bit more problematic.
How hot do brakes get on a really, really high-end braking situation?
950,
it,
1200 degrees Fahrenheit. Like without ducting, you're gonna get into some scorching hot temperatures, enough to where you're gonna see rotors glow.
I would think that if they're glowing, they're past 1600 easy.
It depends. It's a
But they certainly cool down quicker.
right, right, and anyways this thing goes over like the reason why I pulled this sheet up specifically is it goes over if you have a 5-volt reference, you need a 1 kilo ohm pull up. So if our ECU, let's say our particular brand ECU might say we have a 2.4 kilo ohm pull up. Well, in that case, it should be running the 8-volt sensor, which is the closest to this 9 right here. Oh, I'm sorry. It should be running a 12-volt sensor because that would be closest to the 2.4 that the internal pull up would be at. So I believe Haltech is 2.2 kilo ohm.
I think on the crank. I think the crank one is also 1K, but we could check. It could be 4.7. I can't remember.
Yeah,
it's probably in the spec sheet somewhere.
Yeah, so there's a spec sheet for each ECU. This is not too specific, but just something to go over and keep in the back of your mind.
5 volts should be fine.
Yeah, but what I'm saying is for some ECUs, if they have a 2.2 kilo ohm pull up, then you're going to want to run that at a higher voltage to match that for this particular sensor. These are just things that we're looking at from a tuning standpoint that make sense now, so they don't have to worry about them later. It's just kind of the thing with everything else in life. You put the investment of time in, and it will usually come out better. And then this one goes and says distance between teeth, target thickness, tooth height, total width. So this thing goes down to, I think it's 6. Yeah, that's a 30,000th of an inch there. Where did it go? There it is, 60,000th of an inch operating air gap, and the range is not as sensitive for this one. So that's going to be as per your usage. Anyways, do that. We're back to us.
Yeah. So for trigger setups, be patient, scope, take advantage of the tool. It is a godsend. It'll turn a 2-day or 3-day problem into a 5-minute solution. You can easily troubleshoot something with the scope and figure it out immediately and not have to call the manufacturer, post on the forum your problem, wait for an answer, get offered 100,000 options to evaluate when a simple scope will tell you exactly what's going on.
And the thing is that if you shortcome this important step, this is the difference of your engine and not your engine. Now you have a pile of rubble that costs you $25,000 versus you took that 3 hours, 3 days, whatever it may be, finding these faults and whether it's the harness, the configuration, or something that caused a negative thing like this. So just take your time.
You know what? I'm gonna before we go, let me since we've spoken so much about the scope and that
Go ahead
sort
and
of thing.
screen share.
Yeah, I'm going to let me find an image we can use.
So we're talking about oscilloscope, and Claudio's going to be pulling up something that showcases what a standard trace should look like, I'm assuming, of a crank and cam or trigger.
Yeah,
Oh,
let's use this one. This one seems complicated enough. Can you please give me one that's large enough? Here we go. Open. No, come on.
do you see these gray? These grays have been from tuning. Look at this.
The one now?
Grays are from tuning. By the way, this is my day off. Just want to put that out there.
This is your what now?
My day off.
Oh, you have days off?
No.
I hate it when I find what I want. God, this is so annoying.
I should have paused this. These poor people.
Can you? Yeah, you know what? Pause it for a second.
Back.
Hey, okay, another pause unexpectedly. All right, here we go. Just to close off here, let's look at this is from a manual, but it basically represents an oscilloscope trace where we have a cam sensor and a crank sensor. Now, if you'll notice, there are lots of little peaks here and only 3 little peaks here. Now, this is off of more than likely a Toyota, what we call a 36 minus 2. We've got 36 teeth on the crank and a gap of 2 teeth that just repeats. And then for every 720 degrees, we get these 3 teeth. It's basically the spacing of 4, but one of them is missing. Now, if you were looking at this at a scope, you'll notice that, for example, on the crank, the peaks go up and down really fast and really quick, and you ask yourself, what is the edge that I'm supposed to have on this? I know the teeth count, but is it a falling or rising? Well, if you notice here, the missing gap only has a rising edge, which means there's no falling edge, which means that the signal is in fact a falling edge signal because there's no falling edge for the gap. That tells you exactly that the crank sensor is a falling edge signal. On the cam sensor, for example, you do have a falling edge all the time visible. So again, this sensor is also a falling edge. So the reason I say look at what's not here, and it's the opposite, is because obviously if you look at that and you say, well, is it a rising edge? No, the signal is falling because there is no falling for the width of the gap. That's why you say this is a falling edge signal on both these cases, because the signal goes up, goes down past 0, and then up. If this were reversed, then it would go down, then up, and then come back to 0. Then it would be a rising. But both of these are falling. So this is a nice clean. Yeah, go ahead.
What's interesting is the bottom one looks like it purely goes down first and then up and then down again. So it looks like they're swapped. However, I see what you're saying.
it's a bit misleading, but if you think about it in the way of what is my actual correct edge, the gap will
Right.
tell you, because if there's no falling edge, okay, there's no edge to look at or to count. So that's my gap. If you had it set to rising, then you would have a bit of a trigger wobble or an error happening, or a
Gotcha.
timing drift or something along those lines. So think about it when you have a missing tooth. You think about it the way. So am I looking at the gap? I only see it go up, so that means my edge is the reverse. If it
That's
were going down, then it would in fact be a rising, because I don't have the rising edge.
I
And
gotcha.
that's how you view that. Yeah. So once you
Good to
have
know.
that crank and cam edge, a couple of tips based on the edge. An incorrect edge on the trigger will cause a timing drift, smooth in one direction. An incorrect edge in the cam will make it go move and then shift quickly to a different spot or disappear. That tells you which of the edges you may have incorrectly set. When you're doing Hall effect, for example, where there is no drift, what happens is in the cam sensor, the wrong edge is in the wrong position, so you get a shift out of timing, or some switching of the timing mark on the with the timing light. That's how you know your cam edge is wrong. An easy one to miss, for example, would be the Volkswagens, the modern ones with the cam timing, where you have 4 teeth on the cam, 2 big, 2 small, and only the falling edge is the correct one. The rising edge happens here, 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 here. So that's where you get the shift, and that's where you know you've got the wrong edge.
Good to know.
And that's what I had to say about that.
Well, would you like to close this off with we recapped pretty well on that last intermediate video.
Yeah, so importance to trigger, be patient, use the scope, have tools handy, have your timing light. If you cannot tell what the pattern of teeth is, again, use the scope, use your timing light, make sure you know where the engine is got its marks. If the crank pulley, there's some doubt about what you do, what you have, or no crank pulley marks, you'll have to put something on it. If it's not too easy to do, you can always go the rod in the cylinder. But remember, there is a bit of a gap of about 5 to 10 degrees plus or minus that you could have with that method. The cams help to line it up. In the case of a rotary, you got to look in the spark plug hole, and there's also a little bit of a plus or minus there.
There's a plus or minus there, and
Yeah.
there are quite a few different methods. I think there's 4 or 5 different methods of using spark plug holes to locate a rotary engine, most of which I've not found to be perfect. The
So
best
ideally,
way,
you want the right pulley
Yeah.
for the right engine front cover that you have. Oh, that's another one. If the front cover is what's been swapped, the position of your needle is not in the right spot.
Right. And so on the rotary stuff, there are 2 dead to nuts accurate spots all the time. And that'll be if you take off that front hub assembly, you're going to have a Woodruff key that's sitting on. The Woodruff key will be at a 9-degree location when looking at the front of the engine.
Did
9
you say
degree.
9? 9 or 90?
9 o'clock, excuse me.
Oh, 9 o'clock.
9 o'clock position.
So that way.
It'll be a dead away.
Yeah.
Dead away. And besides that, if you have a factory flywheel, there's also a flat spot on the flywheel, which will also dictate the same thing. Most people don't have a factory flywheel that I tune because we're always doing crazy aftermarket stuff at 4 times factory power. So that's another thing. FD's only made about 215 to the wheels, if you really want to think about it. So if you see these setups going out 600 horsepower, it's 3 times over already. Be patient.
Take your time. Use
patient.
the tools. Yeah, be patient. Remember to use the scope. The scope will save you a bunch of time when you don't know what's what. And effectively, once you have it dialed in and you know your timing is correctly set, one last check to do is if the engine's idling, rev it slowly upwards, and you don't want to see any movement at all of your timing mark. It
Mhm.
could wiggle a little. It could drift maybe 4 or 5 degrees in one direction, and that can be fixed using a map called the variable trigger offset map.
Yes. So here, as we're saying that, let me just go ahead and do that real quick.
Yeah.
So now this is something that,
Exclusively for reluctor sensors.
so this TDC offset angle table right here,
Yep.
I just
Yep.
selected it right here. And this can get you in a lot of trouble because on this base table, which is this one right here,
You've got
this
values.
-7 degrees, well, pretty sure, I'm almost positive this is actually advancing the engine 7 degrees at 10,000 RPM.
No, what it's doing it is if it's negative, it'll basically take off timing
Yeah,
from the actual.
it doesn't retard
So,
it. This
well, I
actually,
mean, you could
so
make it positive and it would be going the other way
so what
because this table works 0 plus or minus now. It used to be overall, but now it's plus or minus.
correct. So what I'm saying is because this is a negative value and your trigger is this value here, when you lower this number, this will advance the total timing of the engine. When you raise this number, it will retard the engine further. So what this table is actually doing in
It's,
reality
it's the other
is
way
it
around.
advancing. It is
It's
not
the
because
other way
I
around.
checked it on Dyno the other day. So that's why I
It,
was I caught a car that had a problem and I did not realize this was a tuning issue at first. And now I know for a fact, unless it is a reluctor wheel with any sort of microsecond delay issue on the configuration, I do not use this table unless I have a timing light in person there.
oh yeah, yeah. That the only reason you would is if you have the timing locked, you slowly rev the engine and you get a minimal variation.
Yep.
Reluctors, the nature of reluctor sensors is there will be a tiny variation.
Yep.
And this table serves to undo that. And normally, in my experience, past 4 grand, it's never drifting anymore.
Right.
It's basically kind of up to that point. But you should check it past there to be sure. And never, 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 ever more than 5 or 6 degrees. If
Yeah.
it's 10, 15, or 20 or more, you've got a wired
Something's
sensor
wrong.
backwards.
Yeah.
The
Oh, yeah.
sensor's wired backwards.
So yeah, I just wanted to show that the
Yeah.
reason why this could be seen as convoluted or incorrect, you actually have an ignition misfire. Like, I mean, suffice to say, it could be a knock condition uh, by this advancing the engine. And I actually caught it, thankfully, on E85 on this one particular engine. I said, holy crap, if this was pump gas, I would have just completely grenaded this motor as a tuning fault. And so I'm just trying to put that out there. This should be respected. You do this very carefully, diligently, with a timing light, with the
Yeah.
ignition locked.
And
And
that table, in all essence, before you even start messing with it and the timing light, that table should be 0.
yeah,
And then
100%.
obviously it should be 0. You've got your lock on. Your timing isn't moving at idle, of course. You set it to 2 grand, and then you see if it drifts. Let's say you get a degree. Okay, fine. You go to that RPM value, 2 grand, and you
2 grand.
fix it by a degree. You go to 3 grand. Let's say now you get 2 degrees. You put 2 degrees on here, 4, and so on and so forth. You do it up and up and up until there is no drift. And then that's your last value to project until the end of the table.
Another really cool thing to do when you do this, obviously you don't want this to be at -5 degrees. So when you go do that, you can set this to like 20 degrees on here and a 10-degree split, and that will get you your much safer exhaust temperature as you're measuring this temp, or I'm sorry, as you're measuring this offset. So
But
instead
that's
of,
exclusive if your pulley has the timing notch, the timing marks.
well, if
If
you
you don't
marked,
have any timing degrees,
right,
you have to stick it with the 20 after. That's the problem.
right. So
on a
you can always
custom
make
pulley
notes.
so on a custom pulley that has 0, 10, 20 to one side and 0, 10, 20 to the other, then you can set the engine in a nice, happy 15-degree or 10-degree idle timing, and then you can do the test there. It'll still give you the same results. But if you don't have any timing marks at all, you just have the 20 after, you have to kind of work that one.
Yep.
Yeah. So don't spend too much time on $4,000 at -20, or it'll get hot. It'll get a little hot.
Your neighbors will see it from across the yard, like, why
Yeah.
is that guy's exhaust on fire? I don't get it. So just
Something's burning.
yeah, so, who's barbecuing tonight?
All right, gentlemen. Well, we're going to end this module here. Just a quick note. The next one, we will talk about setting your base ignition timing correctly. Well, we actually discussed it a little bit. But we'll go into the actual coils, dwell, power, wiring, grounding, and all that other cool stuff. And troubleshooting a bit of trigger issues that could be both ignition related or trigger related. What to look for.
That's a really, really good recap. Claudio, always a pleasure, buddy.
Yeah, man.
Looking forward to round number 5 for us.
For some.
Yeah, let's do it.
Especially if the software cooperates.
Yeah. I'll catch you guys in the next one.
Let's go. Bye.
Bye.